In today's lesson, we're going to focus on similarity and transformations. And this is very, very similar to some of the work that we were doing back in the first quarter. In particular, when we started off working with congruence, we saw that with congruence, we had those three congruence transformations where you could have a reflection, you could have a rotation, and you could have a translation. We saw that these three rigid motions do not change a shape's size, and they don't change an object's shape. They just move it around without changing it. Well, our focus now is not entirely on congruence transformations, but on the similarity transformations, and of course, these three things are included with them. If you need to explain why two shapes are similar in the coordinate plane, you are still allowed to use reflections, rotations, and translations because all three of these do not change the shape. The only other criteria that we can throw in is that we are allowed to change a shape's size. Well, back when we were working on movement in the coordinate plane, we had a fourth transformation, and we were very clear that you can't use a dilation to show congruence because dilations change the size of the shape, but that's not a problem with similarity. When we're working with similarity, we know that we're going to have the same shape basically in two spots, a bigger and a smaller version, and all the dilation is going to do is change the size to make those bigger and smaller versions match each other. Our focus then is twofold. We want to say, okay, here's where we've got our beginning shape, apply some of these similarity transformations, especially apply the dilation and say, here's where it gets moved to. Having a beginning shape, draw where it goes. Additionally, if we have two shapes in the coordinate plane, we want to be able to look at them and say, are these things similar, yes or no? In that regard, it's like what you were doing before, but now we're going to use movement to explain why they are similar, yes or no. And we do have a particular emphasis on circles. Every single circle, all circles are similar to each other, and we're going to use movement to show why. So here's our first one. Mostly this is a refresher of how do dilations work. Remember, a dilation has the form where you have to multiply both the x and the y by the exact same number. And since we're multiplying by 3, this was a scale factor of 3. What we're seeing then is this original shape, and all we have to do is multiply every single coordinate by our scale factor of 3. So, splitting this one in red, 1 and 1, multiply them both by 3. You get 3 and 3, which is how we located the point A prime. Same thing, multiply your next coordinates, both of them by 3. 3 times 3 would give you 9, 1 times 3 is 3. That's how we could locate. That's how we were able to locate our coordinates for B prime at 9, 3. Same thing, 3 times 3 is 9, 2 times 3 is 6. That leads us to the coordinates of C prime, and then we can graph each one of them, showing where the shapes wind up going. It's worth noting then, just the behavior that we would see when we are working with a scale factor of 3, the side length that was 1 tall is now 3 tall. The side length that was 2 wide is now 6 wide. All of the gaps, all of the side lengths get blown up or shrunk based on the scale factor. The types of problems that we would ask you to do are like this, where you would have your starting shape, you would apply the transformation and draw the image. This is one type of thing that we would ask you to do. One piece that may be helpful, and I'm clearing some of this stuff out just so that we can see it perhaps a little bit easier. Gaps get moved as well. Please notice that this was originally a gap of 1 to the right and up 1. This gap then, when we apply the transformation, 1, 2, let me get the purple. 1, 2, 3, 1, 2, 3. Since our dilation was centered at the origin, all of the stretches and shrinks are going to be based off distances away from the origin. If we were looking at here, this one, 3 and 2, 3 times 3 would give you 9. 2 times 3 is 6. We can see that these gaps are actually following the scale factor. But of course, that's exactly what the coordinates are supposed to do. Our coordinates 9, 6, they're based on these gaps from the origin, so that's why we've got the shortcut. We can actually count gaps, and that's fine. We can also multiply the coordinates, it's fine. They're two different ways of looking at the same problem. Ultimately, though, we're going to look at problems like this. Given our original shape, P, Q, R, I've got that one, I traced that wrong. Okay, our shape is PQR, so P, Q, and this was labeled incorrectly. That's supposed to be R, because R is here at 4, 4. And then when we take that effect, this is going to wind up being R prime. So, okay. But we can already see, based on the image, where it's going to wind up going. But still want to emphasize a scale factor of 3/4. All you have to do to figure out where it's going to go are take every single one of our coordinates and multiply all of them by that scale factor of 3/4. 3/4 of -8 gives you -6. 3/4 of 4 equals 3. That's how we are able to identify the point P prime. Just multiply the scale factor by each of your coordinates. It wound up right there. And of course, if you've got some scale factors that are tougher to work with, or you have a hard time doing the multiplication in your head, feel free to use a calculator to make sure that you're getting the correct numbers and not accidentally making a mistake. When we multiply through, we get Q prime of -3, 6. Multiply, we get R prime of 3, 3. Just plot the point, applying the rule to all of them, and there we go. We're done. Being able to draw the image of a dilation is one of the skills that you need to have. Of greater importance, because we're focusing on similarity for our entire unit, the more important ones are here. Are these things similar? Yes or no? If the answer is yes, you have to be able to describe how do you go from your pre-image to the image. And it doesn't matter which one you call the pre-image and which one you call the image. You can start with the big and move it to the small. You can start with small and move it to big. That's up to you. For me, unless I'm told the direction, I prefer to start with these ones. Because I would rather work with a smaller one and blow it up bigger, multiplying by numbers that are bigger than one. That's just easier for my brain. Okay, so let's look at it and see if we can't figure out a rule. K is at 1, 1, C is at 3, 3. What scale factor would you need? Obviously, that leads us to a scale factor of 3. So if these things are going to be similar using just the one dilation, we would need our rule to be a scale factor of 3. This would be our dilation. And so we need to check, does this rule work for every single corner? If there's even one corner where it doesn't work, this is not the correct rule. And so we've already checked C and K worked out. What about A with J? Negative 2 times 3 does give you negative 6. 1 times 3, yes, so okay, so A and J check out. And then we're looking at B, which was located negative 6, 6. So negative 2 times 3 gives you negative 6. Negative 2 times 3 gives you 6. So B and H match up. 1 times 3 gives you 3. Negative 2 times 3 gives you negative 6. Also checks out. So yes, this one rule does map all 4 pairs of points together. So because we have used a dilation, yes, we can say A, B, C, triangle. We'd be able to say A, B, C, D is similar to, and then let's make sure that we've got them matched up. A corresponds with J, B corresponds with H, C corresponds with K, L corresponds with D. And so I've written this down, and I would like you to stop and figure out what's wrong with that. There is a problem with the order in which I've written down the points. You need to remember that you're not allowed putting these down in any order you want. I put D there, I meant to write down L. Even with writing down L, it's still wrong. When you write the points down, you're saying this is the order in which they connect. This says you drew your shape from A to B to C to D. That's not our shape. There is a tendency of students to put these things in alphabetical order just because, okay, A, B, C, D makes sense, but you can't rely on that. This shape is not A, B, C, D. It's A, B, then D, then C. The order should have been A, B, D, C when we write up our similarity statement. Otherwise, you're referencing a shape that doesn't even exist, which would allow us to put them in order then with their corresponding parts. This was correct, that one wasn't. Okay, so what do you think? Are they similar? We can still use the same kind of techniques. One piece that can be very helpful when you're looking at these are paying attention to some of the side lengths. You can figure out if it's similar based on just inspection. This piece is a side length of 2. That's a side length of 3. So if we're going to blow them up, we would have to know that we could create a scale factor of 3 to 2. Because side lengths get shrunk and or expanded by the scale factor, we can simply look at lengths like this and figure out what the scale factor would need to be. And so checking for our rule, if they're going to be similar from a single dilation, this has to be the rule. Or we just multiply by 1.5. And of course, if you want to speed up some of the calculations, feel free to grab a calculator and do the multiplication. So when we're looking at this, two zero, if we multiply by 1.5, we get 30. So that point would get moved here. Taking the other points, 2, 4 for point Q. If we multiply that by 1.5, the 3 over 2, we get 3, 6. So that would be here. Point R, 4, 4. If we multiply it by 1.5, we get 6, 6. So 6, 6. And of course, since we're talking about a rectangle, there. What we're seeing, the original shape here in yellow, based on the scale factor, turns it into the red. Now we can continue to use reflections, rotations, translations. We can use our congruence transformations to put these on top of each other, if they're the same size at all, and it's pretty obvious that they're not, because when we're looking at this one, let's fill this one in here and say, based on the scale factor, we can make it bigger, and if we try to do a translation, the width matches up, but it's just plain not tall enough. Since it's just not tall enough, there's no way that we're going to get these two things to match up with each other. These they're not similar. That's it. You can't identify transformations that make them that way because they're not. Don't forget that the behavior of the shape has to stay the same. It needs to be the same shape, just bigger or smaller. Identifying matching components, things that would have to go together, will allow you to find a scale factor. This one would need a scale factor of 3 over 2 to make the widths match, but we're going to check the original. A height of 4 and a height of 10. It would need a scale factor of 10 over 4 to make the heights match. It needs a scale factor of 3 over 2. There, we need two different scale factors to make these match up. And two different scale factors shows us that they're not similar. Here's our last example for the day. No matter where you draw circles, no matter what size you draw them, they are always similar. You will always be able to make circles match up with each other. And basically, it boils down to two steps. You're going to have to change the size using the dilation. And then you'll have to match their centers using a translation. So, how are we going to change the size? And to make this one, I'm going to move from the small one to the big one. If we wanted to, we could go big to small. It doesn't matter either way. The radius of my small circle is 1. The radius of my big circle is 3. We need to change the size so that the radiuses are the same. That tells me I can use a dilation with a scale factor of 3. Centering at the origin, 1, 2, 3. 1, 2, 3. 1, 2, 3. 1, 2, 3. And just drawing in a sketch. Not perfect, but no, kind of ugly actually. We can see then the sizes are matching up. Now we need to move my sketch up on top of the other one. So what kind of translation is going to move it? Well, the centers need to match. So how do I move from my current pre-image center to the image one? 1, 2, 3, 4, 5, 6. And I'm fortunate that I don't need to go left or right at all, so I can simply say translation up 6. There. Now they're on top of each other, showing that they're similar. That's all it takes. Anytime you need to show that circles are similar, it's nothing more than changing the size first with the dilation, and then wherever things got moved, you're going to match the centers by using a translation.